Hello, am I audible? Can anyone please verify? Okay, thank you. Good evening, all, and welcome to the problem solving session of microwave engineering. So, today we are having our session 5, and so the topic of discussion for the week 5 was microwave resonators. So, the content of coverage in this particular topic, as we see in the video lectures, are as like this the series and parallel RLC resonators, then the transmission line resonators, then waveguide resonators. So these are some of the major topics which had been discussed in the video lectures of week 5. So, let me try to brief some of the key concepts in this particular week 5 content. I would request you all to tell me what do you understand about the condition for resonance. So, you can either type in the chat or you can unmute yourself and mm, uh, comment what you think. What is the condition for resonance? So, as we see, so the whole week 5 was about different types of microwave resonators, starting from RLC resonators to transmission line, how it can act as a resonator, then a waveguide, how it can act as a resonator. So, ultimately, the basic concept of what is a resonance or what is the condition for resonance. Please comment in the chat box, or you can unmute yourself. So I think I can give some clues here. So you have come across this XL and XC, which is basically the inductive reactance and the capacitive reactance. So, at the condition of resonance, can you tell what will happen to this XL and this XC? At resonance, what will happen to this XL and XC? Is XL greater than XC, or is XL less than XC, or what is the condition for resonance? So, XL equal to XC is the condition for resonance. Whereas, so the intuitive idea is the energy storage in the capacitive field is same as the energy storage in the inductive field, or we can say the energy oscillates between the electric and magnetic fields at resonance. So that is the condition for a resonance. So so to talk about some of the resonance circuits in the to brief about them so that it will be easy for looking at the numericals. So I hope you remember series RLC, and parallel RLC. So let's start by looking at what is a series RLC resonator. So we have a RLC, which is series connected RL and C, and you have a source. And this is very well known. How do we write the Z in here? How do we write the Z in here? So Z in is, so all these elements are connected in series. So Z in is R plus J omega L minus J 1 by omega C. So I hope you all agree with me on this. So if I try to simplify this, this comes to be R plus J omega L into 1 minus omega naught by omega the whole square. Okay. Here, something to note here is this omega naught is 1 by root LC. Okay. So this is the resonant frequency, omega naught, angular frequency basically. So omega naught is 1 by root LC. So it depends on the L and C connected here. So this expression is reduced in terms of omega naught and omega. So the other important thing to look at is the graph of Z in versus omega, wherein you have seen in case of a series RLC, the input impedance goes to minimum at the resonant frequency, and the value of that minimum input impedance is R. So this is all about series RLC. A similar discussion had been there on parallel RLC also. Parallel RLC network. So in case of a parallel RLC network, as you know, this is R, L and C connected in parallel. So in this case, if you simplify and finally get to the plot of Z in versus omega, that is the plot of input impedance versus omega, you see that it has a maximum impedance at resonance, and that is equal to R. The maximum input impedance is equal to R, and that happens at the resonance. So this is about the series RLC and parallel RLC basics, or very brief idea of what is the series RLC and parallel RLC network. Also, we have come across loaded and unloaded Q factors, which is also a very important topic in this video lectures. So to brief on that, we know about Q factor. What is quality factor is known to us. So what is the basic difference between unloaded Q factor and a loaded Q factor? That is something which we need to, which is a takeaway from here. So in, say for example, I have an external circuit which is having a Q factor QE. So that is your external circuit. Say this is the Q factor of a external circuit. Then you have your original network, which is having a Q factor, okay, without the load connected. So this without load connected, we say that is a unloaded Q factor, Q naught. Now, suppose you have a load, say RL is connected to that circuit, say whatever circuit I am saying. In that case, we call it as a QL. So this is the Q factor when the RL or the load is connected. Now there is a relation between these 1 by QL, that's the loaded Q factor, is equal to 1 by QE plus 1 by Q naught. So this is the relationship between the unloaded and loaded Q factor. Now, in case of a series RLC, let us try to compare both series and parallel RLC. So in case of a series RLC, Q naught is omega naught L by R, or I have one more equation. I can also write it as 1 by omega naught RC. Okay. Now, what is this is the unloaded Q factor. Now, how about the loaded Q factor? So, in case of a series RLC, say for example, let me try to draw it. So, R, L and C, that is my circuit having a Q factor Q naught. To this, suppose if you connect a load, so that load is going to come in series, RL. Okay. So, this is being connected in series to this circuit. So, how do we write QL? QL is omega naught L by R plus RL. So you please note that this RL is coming in series with this R. So that's the reason we just modified it to this. Similarly, in case of a parallel RLC, the unloaded Q factor equation is R by omega naught L or omega naught RC. So the loaded Q factor comes out to be, so in case of parallel RLC, what happens? We have R, L and C, and to this, so this is the circuit having a Q factor Q naught.
Madam,
Yes.
madam, for series RLC,
Yes.
the QL which is equal to that expression is there, no? That we have tried to see, no, madam, capacitor.
No,
R
no.
plus R to C.
You can also write like this 1 by omega naught R plus RL into C. So I have written
Okay,
only one
okay.
equation.
Oh,
Yeah.
yeah.
Okay.
Okay, madam, okay, madam.
So so now coming back to parallel RLC. So how do we write? So as I said, so this is the parallel RLC. To this, I'm going to connect a load RL. So you know that this RL is going to come in parallel with this. So we need to look at a parallel connection of R and RL. Okay. So how do we rewrite this expression? R, instead of R, it should come RRL by R plus RL, because R is in parallel with the RL. Then multiply this with omega naught L. Okay. So this is the loaded Q factor in case of a parallel RLC. I hope this brief will give a idea of how to go to the numericals. So let's move to some of the questions. Coming to question 1, the input impedance of a series RLC circuit operating at 20% above its resonant frequency is given by. So the first understanding is this is a series RLC. So how do we write the expression for Zin? R plus j omega L into 1 minus omega naught by omega the whole square, where omega naught is the resonant frequency and omega is the operating frequency. So, and here we have a relation between them. Can somebody tell me how do we write? So, the operating frequency is 20% above the resonant frequency.
Madam, 20 plus 100 divided by 100.
Yes. Yes, right. So it is 1.2 omega naught. Now this becomes very simple to solve. So can you try? omega is 1.2 omega naught. As you see the options, you have R, L and C as such. So R plus J omega is 1.2 omega naught. L is like that, and 1 minus omega naught by omega will be 1 by 1.2 square. Can we simplify this? I hope you will be able to substitute for omega naught. As I said before, the resonant frequency is 1 by root LC. I hope you might be trying.
Yes, ma'am.
Yes, ma'am.
So, any answers for this part? So, it reduces to R plus J root of L by C multiplied by some constant.
Option A.
Hello?
Option A, ma'am.
Yes. So, option A. So, your answer is 11 by 30 here. So, and the answer is option A. So, let's move to the next question. So, this question is related to Q factor. So, we need to look at this. So, this is a series RLC with an unloaded Q factor. Generally, we represent as Q naught 1000, and the resonant frequency. So this is F naught 200 megahertz. If the resistance is 40 ohm, the question is what is L? The very fundamental equation of unloaded Q factor. Q naught is equal to omega naught L by R. You know what is omega naught? You know what is R? Just calculate L. Q naught into R by 2 pi F naught. So this might not require a calculator. You can notice that the answers are in terms of pi. So
Option D.
Oh, option D. Yeah, right. You are right. So once you simplify this, 1000 into 40 by 2 by 200 into 10 power 6. So it should be 100 by pi microhenry. Or we can write it as 0.1 by pi millihenry. Yes. So okay, now coming to the third question here. A series RLC resonator has a resonant frequency of 500 megahertz. So F naught is 500 into 10 power 6. Unloaded Q is 1000. R value is 200. When a load resistance RL is connected, now this loaded Q factor will become 100. So the question is to find this RL. So you have a series RLC. To this you are connecting an RL. So this series RLC had an unloaded Q factor of Q naught. Once you connect RL, this becomes QL. You know the value of R. You also know the resonant frequency OF naught. Can you find what is this RL connected? So for this we need to use the expression wherein you connect. You need to use the expression for loaded Q factor in case of a RLC, series RLC. So let us write first what is in case of a unloaded Q factor. In case of series RLC, Q naught is omega naught L by R. In QL will be omega naught L by R plus RL. So is there a way to simplify this? We know what is Q naught. We know what is QL. We also know what is R, but we do not know what is L. So, is there a better way to simplify this?
So what is equal to omega naught L upon R? By that, omega naught L I can evaluate.
Okay, so you are saying like from the first expression you find out L and then resubstitute, yes?
Yes, ma'am.
Okay, so yeah, that is one way of doing it. The other way of doing it is take the ratio of these two, Q naught to QL. So then your L and omega naught gets cancelled, and your expression will be R plus RL by R, which you can write as 1 plus RL by R, for which you know Q naught QL and R. Can you find RL? This is an easy way to do it.
Option C.
Yes, right. So 1000 to 100, 1 plus RL by 200. So RL turns out to be 1800 ohms. So this is a similar question. Again, so look at this. It's a parallel RLC. So in case of parallel RLC, please try to use the equation. So the unloaded Q factor, Q naught is 900. The R value in the circuit is 240. Load value is also given to you here, but what is asked is the QL. So first of all, for parallel RLC, what is Q naught? R by omega naught L. Now, what is QL? So because, see, the RL load is going to come in parallel, you have to take R and RL in parallel. So RRL plus RRL divided by R plus RL into omega naught L. So you in this expression, R by omega naught L is nothing but Q naught. So Q naught into RL by R plus R. Any answers here? Okay, you are saying option B.
Option
Yes.
B.
Yes.
Option B.
Option B. Right answer. So Q naught 900 into 120 by 240 plus 120 turns out to be 300. So I have some MCQs here. So the first question is a cavity is what kind of a filter? Is it a low pass filter? So please read this as low pass filter, high pass filter, band pass filter, or a band stop filter. So I hope you remember what is the cavity. So in case, so you remember what is a rectangular waveguide. So if you have a front and back plates of this rectangular waveguide as a shot, then it becomes a cavity resonator. So basically the waves are going to oscillate here back and forth. So that is called as a cavity resonator. So the question here is what kind of a filter it is. This cavity is it a low pass, high pass, or band stop filter? Yes, right answer. This is a high pass filter. This was one of the questions in Indian Engineering Services exam. So in fact, a few questions I have here. So coming to the next question, amounts of time average energies stored in the electric and magnetic fields for the pth mode of a cavity resonator will be. So the question is on the energy, okay? Energy stored in electric and magnetic field, okay? And so it's the time average energy. Is it going to be equal, always equal? Is it going to be equal provided the Q factor is very high? Equal in case of spherical cavity? Equal in case of fundamental mode of oscillation? What do you think is the right answer? So I hope you know that there are multiple modes in a say in case of a rectangular waveguide or in case of a cavity resonators. We know that there are multiple modes of propagation. So the fundamental mode of oscillation, then the multiples of that resonant frequency. So all these are non cases to you. So the question is, this average energy stored in the electric and magnetic field will be equal. Will be equal? Will it be always equal, or will it be equal under some condition? Please type in chat what do you think, A, B, C or D. I think you can type in any options. What do you think? There is no harm in choosing among A, B, C or D. Yes, Arun Raj, as you said rightly, these energies are equal in case of fundamental mode of oscillation. That is basically our resonant frequency. So in that case, as I told in the beginning of the class, XL is equal to XC is the condition for resonance, wherein I told the energy stored in the electric and magnetic fields will be equal. So we can say that the energy is being oscillating back and forth between these two fields, the magnetic field and the electric field. So the answer option is D. Okay, coming to the next question. Again, it's an MCQ. So it's a assertion reason question. So there is a statement. So assertion means you are given with a statement. Reason means for the first statement, there is some reason. So the options are like, you have to say either the statement is true, that is the assertion is true, R is true. A and R both are true if R is the correct explanation of A. Or any of these are true or false. So these are the different options you have. So these kind of questions are quite familiar. So just look at the statement. So we know that greater the Q factor, smaller the bandwidth of a resonant circuit. Do you agree with this statement? If the Q is high, bandwidth will be small. Is this a true statement? Yes. So this is a true statement. Okay. Now, how about the reason? Okay. At high frequencies, the Q of a coil falls due to skin effect. At high frequency, is the Q going to be, that is, at high frequency, is the Q going to be small due to skin effect? So this is also a true statement. Okay. But Now the second part of this, is this reasoning correct? That means Q, the inverse relationship of Q and bandwidth, can you explain with this reason? The answer is no, you cannot explain with that. So it's option B. Both A and R are true, but R is not the correct explanation of A. The inverse relationship of Q and bandwidth has nothing to do with this reason over here. Okay, so now going to another question. So before going to this question, I think I have quite a bit come across some questions in cavity resonators. Basically, they come under the category of waveguide resonators. Okay, now okay, so there is another type of resonators which are called as transmission line resonator. Okay, so that is, we call it as transmission line resonators. A section of a transmission line. Okay, say you have a transmission line of characteristic impedance Z0, a propagation constant gamma, and a particular length of the line L. Okay, so with that, and also you need to say what is the termination, say if it is a open circuit or whether it is a short circuit. So what kind of termination, or is it a load ZL, or is it matched to an impedance Z0? So what kind of termination it is? Okay, so given all these parameters, this transmission line can also act as a resonator. So we need to see what is the input impedance of this. That will determine whether it is a series or a parallel resonator. Okay, so let us look at this question. Again, it is an assertion reason question. First statement, that is the assertion statement. Lambda by 4 short circuited line behaves as a series resonant circuit. Okay. So let us write down, it's lambda by 4 and it's a short circuited transmission line. So you remember, in case of a short circuited transmission line, what is Z in? J Z0 tan beta L. Okay. Here, if I put tan of, what is beta? 2 pi by lambda. What is L here? Lambda by 4. So this simplifies to tan pi by 2. Any answers on this input impedance? What is this input impedance? Tan pi by 2. Tan pi by 2.
Tan pi by 2 infinite.
Infinity. So can you see this? This is coming to be J infinity. So what is the implication of having infinite impedance?
Infinite means open circuit. No?
Yes. So a short circuited transmission line of length lambda by 4, at this point it becomes open circuit. It's transformed to an open circuit. So if you look at the statement, reasoning statement, at a particular frequency, the input impedance becomes infinite. That is true. Now comes the other question. Is it going to behave as a series resonant circuit? Now I think it's clear. Is
Clear,
it
clear,
proceed?
madam. First one is wrong, madam. Second one is correct.
Yes. So this is a false statement and this is a true statement. So A is false, but R is true. So
Option
always
D.
option D. So always try to think with respect to the basics of transmission line and then try to look at the statements given in the question. Let's move to another question. Okay, there are a few MCQs again, so let's try to look at them. So the very first question, the measure of level of coupling between a resonator and a feed is given by. So you have a resonator circuit and you have a feed network. So what is the how do we say the measure of how much it gets coupled? That is being given by what coefficient? Is it a reflection coefficient, a voltage coefficient, or a power transfer coefficient, or is it a coupling coefficient?
Reflection coefficient.
So please remember the terminology used, that is coupling. Now, what is reflection coefficient? If you remember, any transmission line or any network connected to a particular load, okay, say at this point, if this is not same, Z0 is not same as ZL, you have reflection. So at any interface which is not an impedance matched interface, you have reflections. So that is being given by the reflection coefficient. But now here the question is not about this kind of a scenario. Question is about a resonator. Say it could be a series RLC, it could be a parallel RLC, and it is going to be connected to a feed. So how much will be the level of coupling between those two? So that is given by a coupling coefficient. So again, a coupling coefficient in terms of you have come across the loaded and unloaded Q factors, external network circuits Q factor. So if you remember what is a coupling coefficient, coming to the next question, this becomes more clear. What is a coupling coefficient? Is it the ratio of unloaded Q factor to external Q factor? So, Arun Raj, are you trying to answer the question number 5 on the screen?
Yes, ma'am. I put
Yes.
it option
Yes.
A.
Yes. Yes. So, that is the right answer. So, the coupling coefficient, CC, is nothing but the ratio of unloaded Q factor to the external Q factor. This is a true state. So, unloaded Q factor in the sense the original resonator's Q factor. Now, what is the external Q which is being connected? So that is your QE. So the ratio of Q0 to QE is the coupling coefficient. So basically, it's a coupling between the resonator and the feed. Okay, now coming to the next question. What do you think? Direct measurement of unloaded Q factor of a resonator is not possible. Direct measurement of unloaded Q factor of a resonator is not possible. True or false?
Madam,
Yes.
that unloaded queue means without connecting load, we have from using formula we have to find out no directly.
So imagine you have a resonator, either series RLC or parallel RLC.
Well,
So based on the L and C, you can write the expression for a Q factor. That is your unloaded Q factor. Now suppose you connect a load to it. Then it becomes the loaded Q factor.
yes, ma'am.
So the question is whether you will be able to measure direct measurement of unloaded Q factor is not possible.
True, madam.
True. So that's a right statement. Unloaded Q factor cannot be measured because of the loading effect of the measurement system. But from the frequency response of the loaded resonator, you can determine this unloaded Q.
Madam, once
Yes.
again,
But
when I am reading, no.
Yes.
When I am reading, I cannot able to understand, madam. When you are reading, no, at the time I am understanding correct answer. But before that, I put B option in chat box.
Oh, okay.
False.
Okay.
No, madam. But you are reading, no. After that, I think I am understanding wrongly, madam. This question.
Yeah. It's just about understanding the question. So the thing is, we have to connect to what we already know. So then it becomes more clear.
Okay, madam.
Okay. So one more question I have. When the coupling coefficient is 1, resonator is it undercoupled to the feed line? Is it overcoupled? Is it critically coupled? So you have a resonator and you have a feed line. So suppose if the coupling coefficient is 1, that means it is a critically coupled. Yes, right answer. So if the coupling coefficient is less than 1, then it is undercoupled, and if it is greater than 1, it is overcoupled. Okay. So just wanted to give some questions. These are some of the questions, sample questions taken from multiple examinations, basically Indian Engineering Services exam and some other exams. Okay, now coming back to numerical, let's try to solve it. This question is from a cavity resonator. So as you see, it's a rectangular cavity resonator. It's an air-filled cavity resonator. So I hope you remember. So these two plates are basically shorted. Then you call it as a cavity resonator. And this is the dimension, 3 centimeter and 2 centimeter. It has a dominant resonant mode frequency of 6.25 gigahertz. The question is, what is the internal length of the cavity? So I hope you understand what do you mean by the length of the cavity. So this is your length of the cavity, L. Okay. You are given with the dominant resonant mode. So now the question is, how do we write the expression for resonant frequency, and also which is the dominant mode? In case of a cavity resonator, I hope you might have come across this equation. C by 2 into square root of m by a the whole square plus n by b the whole square plus L by d the whole square. Okay. Now, which is the dominant mode? Any idea? Which is the dominant mode in a cavity resonator?
TE10, madam.
101.
Yes, exactly. So just use that. So in this case, m equal to 1, n equal to 0, L equal to 1. Just substitute the value of Fc and A and so n goes to 0. So this parameter is 0. So you already know what is A. What you need to find is basically just don't confuse with this L here. So in this expression, this is basically TEMNL. Okay. So this is length of the cavity is nothing but the D. So this is A, this is B, and length of the cavity is D. M and L are the indices. Okay. So please don't confuse. Can you try 6.25 gigahertz? C by 2 into square root of 1 by 3 square plus 1 by D square. You need to find what is D. So please have a look at the answers. All answers are in centimeters. So it's always convenient to substitute in centimeter. So please take care of that here also. C value in centimeter per second. When you get the answers, please type in the chat. Okay. So yeah. So as Amit, you are right.
4
It
centimeters.
is 4 centimeter. I hope you might have substituted this is directly as 3 into 10 power 10. So then you will get the answer for D directly in centimeters as 4 centimeter. So let's move on to the next question. Okay, there's a small correction. So, okay, the short circuited half wavelength transmission line has its first resonance at a frequency of 200 megahertz. The attenuation constant of the line is given like pi by 500 Napier per meter. Velocity of wave propagation is 2 into 10 raised to 8 meter per second. Please read it as 10 raised to 8. The question is unloaded Q factor of this resonator at its first resonance. Okay, so see, this is a question from transmission line based resonator. Okay, so as we discussed even in the transmission line section, a short length of a transmission line, say length L, with a characteristic impedance of Z0 and propagation constant of gamma, and whatever be the termination. So this might act as a resonator under certain conditions, depending upon the length of the transmission line and depending upon the termination of the transmission line. So here it is mentioned that a short circuited transmission line, and what is the length of the line? L is lambda by 2. So it has a first resonance, okay, F0, that is at 200 megahertz. What is given is the alpha, the attenuation constant, pi by 500. Now, the velocity of propagation is 2 into 10 power 8 meter per second. Can you find the unloaded Q of this resonator? How do we find a Q naught? So, if you have gone through the video lectures, you might be remembering what is the expression for Q naught. Can you remember what is the expression?
Pi by 2 alpha L.
Yes, exactly. So it's pi by 2 alpha L. Okay. So it's a short circuited line with L is equal to lambda by 2. This is the expression for unloaded Q factor. Any idea if the length is lambda by 4, what will be Q naught? If the length is lambda by 4, short circuited transmission line with length lambda by 4, what is Q naught? It will be pi by 4 alpha L.
4 alpha L.
Yes, yes. Okay. So just giving an idea of that. Okay. Now, so are we, do we know what is alpha L? Do we know the length of the transmission line? Alpha is not. Do we know the length of the transmission line? Or is there a way to find the length of the transmission line?
Lambda, which is equal to C by F, no?
Oh, lambda is C by F. Okay. So
And then we'll find.
do you think that it is C is 3 into 10 power 8?
No, madam. Here
So
2
this is
into.
so we can't say C. Basically, the velocity of wave propagation we have to consider. So basically, we have lambda is equal to Vp by F. Am I correct? But
Yes, ma'am.
my question is, how do we find the length of the transmission line? Because this parameter is length, right? Okay, sorry, length is given as lambda by 2. Okay. So pi by 2 alpha, and the length is, sorry, lambda is Vp by F. So 2 gets cancelled. Pi divided by alpha is pi by 500 into Vp is 2 into 10 power 8. Did we miss something? I think yes. Lambda. Okay, I missed frequency F. So F will be here 200 into 10 power 6. So the final answer will be yes.
Say
So the
500.
500. Yes, right answer. So it is 500. So, is there any doubts from the week 5 content or the previous weeks? Any of the content or assignment questions? Just
Madam, previous weeks, third questions,
okay. Can you
I
tell
can't
the
understand.
which assignment?
Last assignment, madam. Week 4, third question, matching network, madam.
Okay, week 4, question number 3. Yeah. Okay.
Yes, madam. I thought that is it not,
Question
but
number third.
correct.
Okay. Let me
But
just
the answer is it not by 2?
week 4, third question. Okay. 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 So for this question, accepted answer is Z naught by 2.
But is it not, no, madam, answer? Wrong.
Z not answer, ma'am.
Oh, okay. Can you share if you have already solved?
Madam, I will mail you, madam. Mail ID.
Okay.
I kept in college, madam, that solved notebook.
Okay. 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 So,
I will send you mail, madam, that questions.
okay. Okay.
But I think I done mistakes, I know, na? But
Mm. Okay. Right now I haven't. I don't have the solved thing. Okay. You can email me the solution. So I'll
okay,
check and get back to you on this. Week 4, question 3. Okay.
okay, madam.
Ma'am,
Yes. Please.
please give me email ID, ma'am.
Yeah. Okay. Yeah. You can check the chat box for my email.
Madam,
Yes.
one more doubt. What is the difference between log and LN, madam? I don't know. This is basic questions, but I don't know, madam.
Okay.
Log
Okay.
and LN log is there, no, madam.
Oh.
Last class when formula came.
Okay. 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 So, there is something called as um, so the what do you call it's the index, the logarithm to the base. Sorry, logarithm to the base 10 is generally denoted as log, whereas logarithm to the base e is denoted as ln. So generally this won't be mentioned. It will be just ln. So sometimes it will also be mentioned as log to the base e. Okay. So suppose if I want to write something like log 10 x is equal to y. Okay. So how do I write x is 10 raised to y. Okay. Whereas if I write ln x is equal to y, if I want to write x, that will be e raised to y.
Okay, madam. This one only I
So-
need. Thank you, madam.
Okay, so this is the basic idea of logarithm and like logarithm to the base 10 or to the base e.
For this answer, I don't know, no, madam. That we are using first one, madam. Ln of x.
Okay.
I don't know how to remove. One question I wrong, madam. Last is.
Okay. So you can
Thank
use
you, madam.
this expression.
Okay. That binomial is there, no, madam.
Oh yes, right. The last.
I don't know, madam, how to remove. So I one answer wrong, madam.
Oh, okay. I
Okay, thank you,
think
madam.
there was a question which I discussed in the last session.
Yes, madam, discussed it, but you told the answer, but I don't
Okay.
know how to take this LN.
ln. Okay.
Yes,
I
madam.
think in calculator it is clearly mentioned like ln, right? So you can distinguish in the calculator itself, I think, ln and
Is there, madam, but here
ah.
same thing. I need to find out x value.
Okay. Understood. Okay,
Okay,
binomial
madam.
transfer. Okay.
Yes, madam.
Okay. Got it.
Okay, thank you, madam.
Okay. Any other questions or doubts you have?
No, madam. Only one suggestion, madam.
Ah.
Uh, this video we have to post within 1 or 2 days, madam.
Yeah. So unfortunately, last week's video I couldn't upload. I mean,
Yes, madam.
I was
Today
doing
only I
that.
got it.
Yes, understood. So it was very unfortunate. Like it was missed. So from next week onwards, I'll take care of that.